So today I'm going to introduce you to reactions, but we're really going to focus on alkenes because they're going to help us do so. Let me explain why. In general chemistry, we've learned that reactions always happen when there's a collision between two reactants that have the right energy and orientation. And that's true. But however, in organic chemistry, usually it's a collision between something that has a lot of electron density and something else that doesn't have very much electron density. And the thing that has electron density donates those electrons, or partially donates or shares those electrons with the thing that does not have that electron density, and forms a new covalent bond. Remember, in general chemistry, you have ions usually that are just recombining and sticking together in different ways. However, in forming soluble or insoluble mixtures. In organic chemistry, we're generally forming new covalent bonds or breaking covalent bonds. And this happens from something that has electron density sharing with something that doesn't. Now, what's a great example of something that has a lot of electron density? Well, that'd be alkenes. So that's why we're going to start with alkenes, and you'll see what we find that has very little electron density. It's generally something with a very strong dipole or a charge. So let's go ahead and get started. Now, first of all, I'm just going to draw you a simple propane. There's a propane, right? 3 carbons, 1, 2, 3, and they all have hydrogens. Now, let's review. What does a pi bond or an alkene look like? Let's take a look. So if we take two orbitals, like p orbitals for example, and they overlap each other horizontally, that's going to end up forming what we call a sigma bond. Sigma bond comes from that overlap. If we take two p orbitals and we have them line up like this, so we get that electron density sharing between those aligned but not overlapping orbitals, that forms what's called a pi bond or a double bond. All right? These pi bonds have all this electron density sticking out away from those sigma bonds. So again, this is what we call a pi bond in an alkene. So what that looks like, if we were to just draw that here on our propane, is we would draw it like this. Let me shrink this down a little. It's a little bit big here. And here we have what we call a propene, right? We have turned this from a propane, and we have turned this into a propene. This propene now is going to be great at reacting because we have all this electron density out here in that pi bond that wants to go find something. So now let's look at what probably the easiest example of something it's going to react with, which is going to be an HBr. All right, if we look at an HBr, we remember that the Br has all of these electrons around it, and it's very electronegative, and a hydrogen is just a proton. So it actually has no electron cloud except for this bond. So for that reason, there's a really strong dipole in this direction. This is a really, really positive hydrogen. So what we have here is some electrons that want to move over to that hydrogen. Now, we've started to use curved arrows here. So I want to use reactions to introduce the idea of curved arrows. And the idea of arrows is that they always show electron flow. So an arrow should always start. The arrow should always start at electrons that are moving, right? So here's point number 1. And they should always end at the location they're going to. So the arrow is always going to point at the direction, at the place that the electrons are going to. Now, these arrows always should correlate to something in the next step of a reaction mechanism. So I'm going to go ahead and draw the next step for you in a second. But remember these two, whenever I'm grading, I'm always looking to see if the arrow starts where the electrons are starting on one reactant and point at the location they're attacking or going to in the other. Now remember, this makes sense because this is a pi bond, a lot of electron density, going to where there's a very positive charge. Now this reaction right here can be drawn with another step. And what's the step that we're going to have here? We're going to have a new bond formed. Now there's an important thing that's happening here. What the second thing, or the third thing I'm going to look for, I should say, the third thing I'm going to look for is wherever an arrow ends, there should be a new bond or pair of electrons. So if the arrow ended right here on this H, on the right hand side over here, I should see this should correlate with a new bond. Or it could be a lone pair of electrons. Let me show you what that would look like. Well, hey, you can't just have bonds disappear, so what happened to that Br? Well, you also can't have two bonds to an H. So as these electrons are attacking the H, remember this Br is really, really electronegative. The electrons are also being pulled towards the Br. So you should draw another arrow here, meaning that bond, those electrons in that bond are being pulled towards that Br. Now, what would that mean? I should have a Br that still has its 6 electrons, but now what have we gained? We have gained a new pair of electrons. So again, right here, you're seeing in both of these locations, what I've circled in purple, where the arrow is ending, you see a bond or a lone pair of electrons where they have gone to. So this is how reaction energy diagrams go. They show with arrows the flow of electrons that makes organic reactions happen. Remember the rules. Arrows start where the electrons are that are going to attack. The arrow ends where the electrons are going to. And in the next step, wherever the arrow ended in the previous step, you should see either a lone pair or a bond on that location. So those are the basics of drawing a reaction mechanism. So we've introduced now reaction mechanisms, one of the core ideas of this class, and something we're going to need to get very good at doing. All right. Now, this reaction isn't over because you'll notice there's something missing here. When I made this new bond, I now have a Br negative, don't I? Right? And what else do I have on the previous one? You should pay attention to the fact that this is actually a carbocation. That is a positive carbon, a carbon, cation, positive, right? This is a carbocation. Why? Because look, it had 3 bonds to it here, and now it only has 2, meaning there were only 2 hydrogens on there. So this is currently only has 3 bonds to it. It's a carbocation, all right? So this means that we now have another negative and another positive. So we have another step to this reaction. These electrons right here on this negative are going to flow into that positive right there, that carbocation. And we're going to get a new step. So let's go ahead and draw that right here. All right, so that is the process of this reaction. We've drawn the different steps. Now, we're going to talk, we've now learned the basics of arrows. We're going to need to start talking soon about the energy involved in each of these. So that will be the next step as our foray begins into organic reactions.